Gram-Schmidt hands you an orthonormal basis for any subspace, two perpendicular vectors, both of unit length, clean, but apply a matrix A to that basis, and the output vectors almost never stay perpendicular, stretches them, rotates them, skews them out of alignment. Here's the question that defines the singular value decomposition. Does a special orthonormal basis exist that A maps to another orthonormal basis? Two bases linked perfectly by one matrix. To answer this, recall the case we already understand. When A is symmetric and positive definite, the spectral theorem gives A equals Q lambda Q transpose. The columns of Q are orthonormal eigenvectors. Lambda is diagonal, holding positive eigenvalues. One orthogonal matrix Q does the work on both sides. Recall that an orthogonal matrix satisfies Q transpose Q equals the identity, so its inverse is its transpose. The geometry is simple. Acts by rotating into eigenvector coordinates, scaling along those axes, then rotating back. Symmetric matrices are the gold standard. Everything aligns. Now let's drop the symmetry. For a general matrix, non-symmetric or even rectangular, eigenvectors stop cooperating. They aren't perpendicular to each other. Sometimes there simply aren't enough of them to form a basis at all. And if A is rectangular, it maps from one space to a different space, so the very idea of an eigenvector breaks down. The input and output don't even live in the same place. We need a new idea. Not one basis doing double duty, but two orthonormal bases, one in the input space and one in the output space. That's the leap from A equals Q lambda Q transpose to A equals U sigma V transpose. Here is the statement. Every matrix A is square, rectangular, singular, non-singular. Factors as A equals U sigma V transpose. U is an orthogonal matrix whose columns live in the column space. V is an orthogonal matrix whose columns live in the row space. Sigma is diagonal, holding the singular values, non-negative numbers, conventionally ordered from largest to smallest. This factorization always exists. No symmetry required, no invertibility required. The SVD works for everything. The geometric heart of the SVD sits in one equation. A times phi sub I equals sigma sub I times U sub I. Read it carefully, pick the right V's. Orthonormal vectors in the row space. Apply A to each one. The outputs come out orthogonal in the column space. Now normalize each output to unit length, and the scaling factor you put out is sigma sub I, the I's each singular value. So the V's form an orthonormal basis on the input side. The U's form an orthonormal basis on the output side. And A maps each V cleanly onto the corresponding U, stretched by sigma. This is the SVD's defining property. Now let's assemble these vector equations into one clean matrix equation. Stack the V's as columns of a matrix V and stack the U's as columns of a matrix U. Then A times the matrix V equals the matrix U times the diagonal matrix of the sigmas. In symbols, AV equals U sigma. Here's a concrete 2x2 example. If sigma 1 is 3 and sigma 2 is 1, then A applied to the first column of V gives 3 times the first column of U, and A applied to the second column of V gives 1 times the second column of U. Now because V is orthogonal, V inverse equals V transpose. So we multiply both sides on the right by V transpose, and out pops the singular value decomposition, A equals U sigma V transpose. What about the leftover vectors? If A has rank R, only R singular values are positive. The remaining V's sit in the null space where A times V equals 0. They contribute 0 columns to sigma. No problem, the decomposition absorbs them gracefully. And now the special case closes the loop. When A is symmetric and positive definite, the right singular vectors equal the left singular vectors. V equals U equals Q and sigma equals lambda. The SVD collapses back to the spectral theorem, A equals Q lambda Q transpose. The generalization is consistent, nothing is lost. Why does this matter beyond the algebra? Picture A acting on the unit circle in 2 dimensions. Start with the circle and on it the orthonormal vectors v1 and v2. Step 1. V transpose rotates the picture so that v1 and v2 align with the standard coordinate axis. Step 2. Sigma stretches along those axes by sigma 1 horizontally and by sigma 2 vertically. The circle becomes an axis-aligned ellipse. Step 3. U rotates that ellipse into its final position with semi-axis sigma 1 times u1 and sigma 2 times u2. Rotation, stretch, rotation. Every linear map decomposes into exactly these 3 geometric steps. 3 quick clarifications. First, the SVD is not limited to square matrices. It works for any m by n matrix where U is m by m, V is m by n, and the sigma is m by n. Second, singular values are not eigenvalues of A. They are the square roots of the eigenvalues of A transpose A, which means they are always non-negative and always exist. Third, U equals V only in the very special case when A is symmetric and positive definite, never in general. The SVD is called the final factorization because it works for every matrix, and it reveals the geometry of any linear transformation. Eigenvalues describe what a matrix does to its own eigenvectors. Singular values, by contrast, describe what a matrix does as a map between spaces. That distinction is exactly what powers principal component analysis, image compression, and the pseudo-inverse for low-rank approximation.